Hello everyone, welcome back to MACSMIN 2026. So now Surya Majumder, who has started working with our group and will join us as a PhD student in October, will essentially continue Daniel's talk, so based on continuous invariance for crystals, but we'll talk more specifically about continuous invariant-based asymmetries of periodic crystals. Surya, over to you, please.
Thank you, Professor Kurlin, for the introduction. Today, I will present on continuous invariant-based asymmetries of periodic crystals, quantify deviations from higher symmetry. This presentation is based on our forthcoming paper in the International Union of Crystallography Journal. To begin with, I shall first discuss about past approach and relative multiplicity Z prime. Z prime is defined as the number of symmetry-independent molecules in a crystal structure and can discontinuously change under tiny perturbations. This makes Z prime unreliable for a practical detection of symmetry. Almost any noise can arbitrarily scale up a primitive cell and discontinuously change the relative multiplicity Z prime of a crystal structure. Molecules are represented by Y graphs in the pictures that we can see on the slide. On the left-hand side, the picture depicts a crystal structure whose unit cell contains only one molecule, and the unit cell is colored by the yellow region. If we take the vertical half of this unit cell and apply symmetry operations, we get the full unit cell. So the Z prime of this crystal structure is half. After introducing some tiny noise in this crystal structure, we get a factor 2 scaling of the crystal structure whose unit cell contains two molecules whose terminal vertices have initial positions shown by red circles. So thus, this perturbed crystal structure has Z prime equals 2. We introduce continuous invariant-based asymmetry to quantify the deviation of a periodic crystal from a higher symmetry form in physically meaningful units, angstroms. Pointwise distance distribution of a periodic set can be computed by first assigning k as the number of neighbors, then by calculating the distance to these k nearest neighbors from a certain point in the motif. By repeating this process for each atom in the motif, we shall get the distance to k nearest neighbors as vector rows. A weight is also assigned, indicating the number of appearances for a certain row. If two rows have the same distance to k nearest neighbors, they are collapsed into one row, and the weight is updated as the number of appearances for that certain row over the number of total rows. This resulting unordered set of vectors of k increasing distances with weights is called the pointwise distance distribution. PDD representation has ordered columns as increasing distances, but unordered rows since the motif of a periodic point set is unordered. Point packing coefficient of a periodic point set in Euclidean space, in three-dimensional Euclidean space, is expressed as the cubic root of the volume of the unit cell over the number of points in the motif multiplied by the volume of the unit ball in R3. PPC is defined as the cubic root of cell volume per atom, where each atom is of 1 angstrom of radius, or can be interpreted as average radius of balls packed inside the unit cell. The distances in each row of PDD asymptotically increase as PPC multiplied by the cubic root of the kth neighbor. The pointwise deviation from asymptotic is the unordered set of vectors of adjusted distances obtained by subtracting PPC multiplied by the cubic root of the jth distance in each vector of the PDD representation. We have taken an example in the slide to produce the PDA results. We have taken the periodic point set as the set of integers. Now we can calculate the PDD on this periodic point set by setting a motif and k equals to 4 as we have set in this example. So the PDD consists of 4 distances from any point of z, example 0, to its 4 nearest neighbors, and we get the PDA vector as 1, 1, 2, 2 with a weightage of 1. For the set of integers, we take the unit cell as the interval 0 to 1. Since the motif consists of only one point, which is 0, and the unit ball in R has length of 2, we can calculate the PPC of the set of integers in the following way, and thus we obtain with half. We can now calculate the asymptotic terms by simply multiplying PPC with the jth distance since we are dealing in 1 dimensions. And finally, we can calculate the adjusted distances by subtracting these asymptotic terms from the PDD vector, and thus we obtain the PDA vector, which is half 0, half 0 with the weightage of 1. Now I shall introduce the continuous invariant-based asymmetry. Let an asymmetric unit of a periodic crystal consist of a single molecule. Then we define the CIA of that crystal structure to be 0 because all molecules are geometrically equivalent. If the asymmetric unit consists of two molecules B and C, then we define CIA of that crystal structure as earth mover's distance between the unordered pair set of vectors for all points P in B and the unordered set of vectors for all Q in C within their PDA. If the asymmetric unit consists of M molecules, then we define CIA of the crystal structure as maximum over J and minimum over I of the EMD between BI BJ. The optimal molecule, Bi, acts as a center, minimizing a deviation to its maximum perturbation, Bj. So CIA of a crystal structure measures the minimum perturbation that makes all molecules of a crystal structure geometrically equivalent within that same crystal structure. We can see an example of a perturbed periodic sequence in this slide. We continue with the previous example where we had taken the periodic point set as the set of integers, and now we perturb this sequence by a motif. So the extended periodic sequence becomes the expression which is given by Z epsilon. For k equals 4, the 4 rows of PDD are given by these 4 vectors, where the first vector are the 4 nearest distances from 0, the second vector are 4 distances from 1, the third, the distances from 2 plus epsilon, and the fourth, the distances from 3 plus epsilon. For this, we take the unit cell as the interval 0 to 4. Since there are 4 points in the motif, we take m equals 4, and we have already seen on a previous slide that v1 equals 2. So we calculate the PPC of this perturbed periodic sequence, which is half, which is the same as the PPC of the set of integers. So again, the asymptotic terms are half, 1, 3 over 2, and 2. Subtracting these asymptotic terms from the PDD representation, we get the PDA representation, which is shown on this slide. The root mean square distance between the two distinct rows is given by the RMS, which is epsilon over root 2. We have omitted the weight column since each PDA vector in this representation has equal weight, which is 1 over 4. And since each PDA vector has equal weight, the earth mover's distance between any two distinct PDA vector coincide with their RMS distance. So the pairwise earth mover's distance matrix is given by the symmetric matrix on the slide. We can ultimately compute the CIA by taking the maximum value over the columns from the symmetric matrix and the minimum value over all these maximum values. Therefore, we can say that CIA of this perturbed periodic sequence is epsilon over root 2. An isometry is a distance-preserving transformation, such as translation, rotation, reflection, or their composition. If S and Q are two periodic point sets are said to be isometric, it implies that all distances are preserved in these sets. Since crystal structures are determined in rigid forms, they can be efficiently separated as rigid classes by quickly computable invariants, which are numerical properties preserved under rigid motion. Where an invariant is defined as a function which takes the same value on all rigidly equivalent crystals, so crystals can be distinguished using invariants. CIA is invariant under isometry and independent of an asymmetric unit of any periodic point set. Let S be a periodic point set and let Rs denote the minimum half distance between any points of S. For any epsilon greater than 0 and less than this minimum half distance, let Q be obtained by perturbing every point of S up to a Euclidean distance epsilon. Then the CIA based on PDA for any k greater or equal to 1 satisfies the absolute value of CIA of S minus CIA of Q is less than or equals to 4 epsilon. The continuity and invariance of CIA are thoroughly proved in our paper. Crystal structure prediction aims to predict optimal structures computationally but often produces too many local optima approximations and fails to reliably identify near duplicate structures. This overprediction makes simulations time and resource intensive and often requires manual visual inspection during subsequent results analysis. Here we have analyzed 4 CSP datasets in our paper of simulated crystals based on the molecules T0, T1, T2, and T2e, which are shown on the next slide. This table corresponds to the name of the 4 CSP datasets and the number of all of the crystal structures present in these datasets. This CSP study reported energy density landscapes and about 7 experimental crystals, which substantially extended the small population of nanoporous crystals in the Cambridge Structural Database at that time. Now I shall discuss the CIA values on these 4 CSP datasets. On the left-hand side of the slide, we can see the 4 molecules on which these crystal structures were predicted, and on the right-hand side, their CIA histograms are given. The y-axis represents the number of crystal structures in the log scale or as powers of 10, and the x-axis represents the CIA values. The first bin in each plot, which is also dominant in each plot, corresponds to the value of 0 for CIA, and each subsequent bins increase as steps of 0.01. All structures in these 4 CSP datasets were generated with z prime equals 1, but a final energy minimization allowed this symmetry to be broken. So we can see that many predicted crystals are highly not symmetric, and we can say that these structures are unlikely to be synthesizable. This slide shows some statistics of the 4 CSP datasets. The name of the 4 CSP datasets and the number of crystal structures present in these datasets, as we have already seen on a previous slide. The number and percentage of crystal structures having CIA greater or equal to 0.001, the maximum CIA values in these datasets, and the Pearson correlation coefficient between energy, density, and CIA. From the correlation values, we can conclude that CIA provides independent geometric information beyond energy and density. This slide shows the energy versus density plot for T2 predicted crystal structures. The y-axis represents energy, the x-axis represents density. Each point in this plot corresponds to a T2 predicted crystal structure, and they're colored by their respective CIA values, where the color bar is shown at the right-hand side of the plot. Bright red colors correspond to the crystal structures which are highly symmetrical. So energy alone does not guarantee synthesizable structures. This slide shows the CIA versus density plot for T2 crystal structures. The x-axis represents density, the y-axis represents CIA. Density is a fast and continuous invariance. Also, real crystals tend to be more dense. Each point in this plot are colored by their respective energy value, where the color bar again is shown at the right-hand side of the plot. The bright red markers of different shapes represent the experimentally obtained T2 crystal structures. We can immediately see that all of the experimentally obtained T2 crystal structure are perfectly symmetric, having CIA equals 0. This behavior is also zoomed and shown at the top right of the plot. We can also see the apparent independence between CIA and density on this plot. Also for T0, T1, and T2e crystal structures, all of the experimentally obtained crystal structures are perfectly symmetric, having CIA equals 0. This slide shows the average running times in seconds of CIA on 4 CSP datasets versus the number of molecules in their asymmetric units. The y-axis represents runtime in seconds and the x-axis represents number of molecular components. If G denotes the number of blocks in the asymmetric unit and each block contains at most m points, CIA can be computed in time O of G squared m cube log m. And if the asymmetric unit consists of m single point blocks, then the time is O of m cube. So CIA computation is efficient and scalable to large datasets. Now I shall discuss about some important crystals in the CSD with CIA equals 0 and highest Z prime. The first 3 crystal structures in this table correspond to the crystal structures in the Cambridge Structural Database, which have CIA equals to 0 to 3 decimal places, in spite of having 2 or more molecules in its asymmetric unit. And the last 3 crystals in this table correspond to the crystal structures in the Cambridge Structural Database, which have highest Z prime. The pictures of these crystal structures are shown at the right-hand side of the slide. Many crystals with high Z prime in the CSD are close to highest symmetry forms due to low CIA values. This slide shows the histogram of integer numbers G for all 69,196 periodic crystals in the Cambridge Structural Database that have 2 or more chemically equivalent blocks in their asymmetric units. The y-axis represents the number of crystal structures on a log scale. The x-axis represents number of molecules in an asymmetric unit. From this plot, we can see that almost 70,000 of the crystal structures in the Cambridge Structural Database have 2 or more chemically equivalent molecules in their asymmetric units, and the number can go up to 32. This slide shows the histogram of CIA on the log scale with bin size 0.01 angstroms for all 69,196 periodic crystals in the CSD that have 2 or more chemically equivalent molecules in their asymmetric units. The y-axis again represents the number of crystal structures on a log scale, and the x-axis represents the corresponding CIA values. From this histogram, we can see that many of the crystal structures in the Cambridge Structural Database can be in higher symmetry forms due to low CIA values. To summarize this, CIA provides a continuous and physically meaningful measure of symmetry deviation. Many crystals in the CSD show low CIA, indicating near symmetry despite Z prime greater or equal to 2. CIA is computationally efficient and scalable to large crystal structured datasets, and it provides a geometric invariant complementary to energy and density. These measures help understand the relationship between theoretical predictions and experimental observations by finding the most likely synthesizable structures. Thank you for your attention. I'm happy to answer any questions.
Thank you, Surya. Yeah, stop the recording as usual and invite